Hi everyone. In this video, we are going to start our chapter on radicals. So if you have the third edition of the textbook, this is chapter 10. If you have the second edition, this is chapter 11. So down below, I just have a figure showing a typical radical reaction. And if you covered radicals in general chemistry, then you might be a little bit familiar with these three steps that occur: initiation, propagation, termination. If not, don't worry, we're going to cover it again. But the main idea here is a radical, like this one shown, has one single unpaired electron somewhere on it. This could also be a molecule, like down below you see CH3 with a single electron on the carbon. So that signifies that, again, there's one unpaired electron on the molecule or the atom. And this goes through some really interesting chemistry because we no longer have the lone pair that we're used to. We only have a single unpaired electron there. Now, the other lone pairs on chlorine, for instance, are still there. They still exist, but instead of a final lone pair on the right-hand side there, we just have a single unpaired electron. So that is our radical. Now, radicals are very unstable because, again, electrons like to be paired. So radicals will go through many different types of reactions because they're so unstable and very reactive. Okay, so again, we'll go over these steps in the future, but I just kind of wanted to remind you of these if you've already seen them before. So let's introduce radicals. Now, so far, we've only talked about heterolytic cleavage. Now, heterolytic cleavage involves the movement of two electrons to one atom to form ions. So in this example, I have X and Y covalently bonded, and I'm moving the electrons in the covalent bond to the X atom. So it becomes negatively charged, and now the Y atom is lacking electrons, so it becomes positively charged. So again, in heterolytic cleavage, we're moving both electrons to one atom, and we're creating an anion and a cation. Now, in homolytic cleavage, which is what produces radicals, we have the same atoms, let's say, covalently bonded, but instead of moving both electrons, we're going to move one electron to the left, and then the other electron will go to the right. So now each of those atoms will have an unpaired electron. So homolytic cleavage is the movement of individual electrons. Now, you might have also noticed I'm using different arrows to show the movement of two electrons versus one electron. So if an arrow has two barbs or it has a regular heading there, then you're showing the movement of two electrons. But if you only draw one half of the arrow, so it kind of looks like a little fish hook, in fact, people will call that a fish hook arrow, then that's only the movement of one electron. So we'll be using a lot of fishhook arrows in this chapter, so I just wanted to introduce you to that. But again, that's called homolytic cleavage, when you move individual electrons to separate atoms. So let's look at an example. Let's say we have a carbon atom bonded to three alkyl groups, which I'll represent with R, and a halogen, which I'll represent with X. So again, R is an alkyl group, X is a halogen. So that could be chlorine or bromine, for instance. And let's say we have homolytic cleavage of the carbon-halogen bond. What we'll end up with is a carbon atom, still has its R groups, and I'm going to show this kind of from the side of the carbon atom. And then it actually will end up with a p orbital that has a single electron in it. So I'm looking at this from the side, and this is actually a trigonal planar geometry. So we could draw it from above, but then you can't really see the p orbital because the p orbital is kind of above and below the carbon there. So I'm just drawing it from the side to show you what that looks like. Now, what is the hybridization of this carbon? So it's bonded to 3 groups. So would it be sp, sp2, or sp3? sp2. All right. And I'll just also make a note here that that's a p orbital above and below the carbon. Then our other product would be the halogen radical. Now let's talk about the stabilization of radicals. And this is very similar to carbocation stability. So this is super easy to remember because we've already learned it. So if you have, for instance, a carbocation or a positive carbon next to a single bond that's next to a double bond, that can give you resonance structures, right? So that is even more stable than, say, a tertiary carbocation. And it's the same thing with radicals. So something that has resonance is going to be more stable than a tertiary radical, which is actually what we drew up above, because the carbon has 3 groups bonded to it, so it's tertiary. And then that will be more stable than a secondary radical, which is more stable than a primary radical, which is more stable than a methyl group radical. Okay, so let's talk about radical resonance just so you can kind of see what that looks like. It's actually really similar to carbocation resonance. So let's say we have an alkene, and I'm going to draw all of the different hydrogens on this alkene. And then I'm going to highlight the hydrogens on the left in yellow. I'll highlight the hydrogen in the middle in blue. And then I'll highlight the hydrogens on the right in red. And if you don't have a highlighter, you could also label these as A, B, and C, just to show the different hydrogens. Okay, now just as a reminder, the carbons on the double bond here, or the carbons in the double bond, those are called vinylic carbons. So any hydrogens that are bonded are called vinylic protons. And then if a carbon is adjacent to a double bond, then that's called an allylic carbon. So any hydrogens bonded to that carbon are allylic protons. So they're adjacent to a pi bond. Okay, just as a reminder, so if I use those terms, you'll know what I mean. So now, let's say we go through a radical initiation step, which means we're going to produce some radicals. And let's say we're losing one of the yellow protons. So I'm going to show my fishhook arrows, and one electron is going to the yellow hydrogen, the other electron is going to the allylic carbon. Okay, so we're losing a yellow hydrogen that is now a radical. It has a single unpaired electron. Okay, so what would the resulting product look like? So now we only have two yellow hydrogens, and we have a single unpaired electron on that allylic carbon. And then all of the other hydrogens stay the same. So I'll just highlight them the same way I highlighted them before. Oops, there we go. Now, this kind of looks similar to our discussion on carbocations at the very beginning of last quarter. So imagine that that single unpaired electron is actually a positive charge. We're really familiar with resonance in regards to carbocations. Well, it's the same thing with radicals, except we're just going to draw the arrows a little bit differently here. So let's show the movement of this single electron to another carbon. So what can happen with radical resonance is if you have a single electron next to a single bond that's next to a double bond, you can see movement of that electron over to the carbon on the right. Now notice that I drew a fishhook arrow from the single unpaired electron down to the single bond, and then I drew a fishhook arrow from the double bond over, so that's going to actually create a double bond on the left. And then you'll notice that I was splitting apart that double bond, so now there's only a single bond left. And then all of our hydrogens stay the same during this process. But now our single unpaired electron will be on the carbon on the right-hand side. And let me just highlight all our hydrogens here. So again, this looks very similar to carbocation resonance, except instead of a positive charge, we have a single unpaired electron. And we have to draw fishhook arrows instead of regular arrows. Now again, these are resonance structures, so we would actually see a hybrid of these two in real life if we could visualize the molecule. Now both of these resonance structures have the same energy, so we would call these degenerate resonance structures. So remember, degenerate just refers to the fact that they have the same energy. Okay, so let's practice drawing these fishhook arrows for resonance structures. So I'm going to give you a radical. And I would like you to practice drawing the resonance structures for this radical. And remember to use those fishhook arrows, and you can reference the previous slide if need be. But feel free to pause the video so that you can practice first, and then we'll go over it together and you can check your answer. Okay, so let's go over this together. So again, I have a single electron next to a single bond next to a double bond. So that is perfect for resonance. So I'm going to show the double bond breaking apart, and I'm going to show one electron moving up to form a double bond with that single radical electron there. And then the other electron from our double bond will go onto the carbon to the on the other side. So that's going to give us our second resonance structure. So we moved the double bond up, and then we saw that our radical electron is now on that carbon on the bottom right of the ring. Now, looking at this structure, it looks like we could move the electron one more time, because again, now it's next to a single bond next to a double bond. So let's show that. So I'm going to break apart the double bond that's next to the single bond. And then I'm going to show the single electron teaming up with one of the pi bond electrons. So notice you can draw those fishhook arrows above and below to form a bond. That's fine. And now we get our last resonance structure. So we moved our double bond over, and now that single electron is on the carbon on the very end. Okay. So again, very similar to carbocation resonance. If you have a single electron next to a single bond next to a double bond, then you can move that electron kind of like a positive charge, except we're using these fishhook arrows instead to show the movement of electrons. All right. So now let's go over types of radical reactions, and then we'll end the video. So kind of similar to how we covered carbocations, I showed you, or I guess not carbocations, resonance. I showed you the different kinds of resonance situations you could run into. Well, here we're going to talk about types of radical reactions that you might see. So the first one is just simple. It's what I showed you earlier. It's called radical cleavage. So here we're just splitting apart those shared electrons, and we're creating two radicals. Now the opposite of radical cleavage is called radical coupling. So you could have two radicals that team up to form a covalent bond. So radical cleavage and radical coupling are kind of the opposite of each other. Now you could also have a radical and a pi bond, or a double bond. Now the pi bond could split apart, and one of the electrons could pair up with a radical electron to form a sigma bond. So let me actually highlight the carbons on the double bond. So what we did was we created a sigma bond between the halogen X and the first carbon on the double bond. And now the other carbon on the double bond is the radical. It has a single unpaired electron. So we've created one molecule from two different species. All right, so now there's some more types. The fourth type of radical reaction is called elimination, and this is the opposite of addition to a pi bond. So let's say we have that same molecule we drew in the last reaction. Well, this time we could break apart the sigma bond, put one electron on the halogen, and then I'm going to move the other electron over to team up with the unpaired electron, and they're going to create a pi bond. So now we have a halogen radical and our alkene again. So this is the reverse of the addition to pi bond reaction we just saw. All right, the next one is hydrogen abstraction. So we could have some sort of halogen here, and then let's say we have an alkyl group with a hydrogen on it. So we can break apart the covalent bond between hydrogen and that alkyl group and create a new bond with that halogen, or whatever X might be. So now that hydrogen will be bonded to the halogen, and we're left with an alkyl radical. Now, another type of abstraction is halogen abstraction. So let's say we have an alkyl radical, we'll call it, and we have a halogen like Br2 or Cl2. Again, we could break apart that covalent bond between the halogens. One electron goes on one halogen, the other one is going to form a single bond with the radical. So we end up with the alkyl group bonding to a halogen, and then we also have a halogen radical. So Rx is an alkyl halide, and then the X is our halogen radical. Now you'll notice that the halogens here have to be Br2 or Cl2. Like I've said before, fluorine reacts way too violently and way too quickly, whereas iodine reacts way too slowly. So Br2 and Cl2 are kind of in the middle, so they're the only halogens that really work for this type of reaction. Okay, so now that we've seen all of the different types of radical reactions, we're going to, in the next video, start talking about some of these types. Okay, so I will see you in the next video.